Today we introduce a data structure, priority queue. It has only two operations, insert, that is in queue. The others is dequeue, that is obtain and delete the minimum value. For such a goal, how do we achieve it? For example, we use the linear linked list. There is a pointer to the head. Every time a new element is inserted, it is placed directly at the beginning with a pointer to the head. Then change the head pointer to the newly added node. This operation has nothing to do with the number of nodes, so the time complexity is big O1. Pretty good. However, when we want to delete the smallest node, we need to scan from beginning to end, find the smallest, and then delete this node. Then, because all nodes need to be traversed, the time complexity is big O n, and n is the number of nodes. It will be slower. So today we will introduce another method of using binary trees to implement priority queues called binary heaps. The pie only allows vacancies in the bottom leaf layer, but it must be filled from the left to right. That is, only the right side has vacancies. Such a tree is called a complete binary tree. In the previous phase of the binary tree, it was introduced that the tree height is log n. Next, we will introduce the number of times that log n has passed to complete the insertion or removal of the minimum value. However, each node of the binary tree seems to need two pointers to point to the left and the right subtrees. However, the complete binary tree must be filled in this order. Then, if the serial number is assigned to each node in turn, then these numbers are used as the index of the array. Then those nodes can form an array. That is, the structure of the array is actually stored. But we can understand and operate with the complete binary tree. So, is there any relationship between the two? How to convert between each other? In order to facilitate the calculation, we change the array from 0 to 1 to start. Each node of the binary tree is also added with a corresponding number. These numbers are just for illustration and will not actually exist. Well, let's first look at the root node 1. Its left child node and the right child node are 2 and 3 respectively. Then let's look at node 2 and its left and the right child nodes, which are 4 and 5 respectively, and so on. It seems that the pattern can be seen. If the number of a node is x, then its left child node is 2x, and its right child node is 2x plus 1. Then, conversely, if a node is y, then its parent node is y divided by 2. If y is the right child node, the parent node becomes y minus 1 divided by 2. It's enough to unify the lower limit. This is a conversion tip we need later. Then we remove the number. Since the heap needs to find the minimum value quickly, can it be placed on the top? The child node is larger than its parent node. Then, for this subtree, the root node should also be the smallest, such as this. Such a parent-child node meeting the size order is called a heap order. However, there is no size relationship between the child nodes of the common parent node. In short, any node is smaller than its children. Well, the unique properties of the two heaps are introduced. If the parent node is numbered x, the child node numbers are 2x and 2x plus 1 respectively. Second, any node is smaller than its child nodes, that is, heap order. Can we use them to implement priority queues? The first is how to insert 14. First, insert an element when creating the next space. Then it is found that it is smaller than its parent node, and it does not meet the requirement of the pi order of the node smaller than its child node. These steps boil down to comparing size with the parent node. If the parent node is larger than itself, the parent node will be moved to the current empty position. So dive down its parent node. When we want to insert this blank node again, we see that the 14 is still smaller than its parent node 21. So continue let 21 go down, and then it can be inserted, because it is larger than parent node 13, which satisfies the heap order. So the last step puts the inserted value in the current slot. This is inserted C language code. The main code is here. Let's take a look at the steps just now. First, I refer to the next position where the array is inserted. It is the current total number of nodes plus 1. That is the first step. It is assumed that the array is long enough. Next, the inserted x is compared with the parent node where the slot is inserted. The number of its parent node is I divided by 2. If this condition is met, that is, the inserted x is smaller than the parent node, then enter the for loop. Assign the value of the parent node to the current slot node, and then divide the number I of the insertion position by 2 to become the parent node just now position. Then this is the second step. Until this condition cannot be met, that is, when the inserted x is larger than or equal to the parent node, the for loop is jumped out, and the inserted value is assigned to the current inserted position, I. Then this is the third step. Next, quickly take out the minimum value. According to the heap sequence, the minimum value is the top root node, which is 13. This is straightforward. However, we need to put the minimum value of the remaining nodes on the root node for the next time. How to do it? Its left subtree is also in line with the heap order, which is 14, is the smallest one here. In the right subtree, the same root node, 16, is the smallest. Therefore, the entire minimum value is the smaller value of 14 in the left and the right nodes. Moving it up and put it over is equivalent to moving the empty space down one value. In the final analysis, move the smaller of the left and the right child nodes of the vacancy up. Then, using the same routine, choose the smaller value of 19 among the empty child nodes and raise it up. Then raise the smaller value 26 in the child node up. Okay, so is this done? Think about it. I said before that the heap must be a complete binary tree, where it is guaranteed that the leaf nodes must be filled from left to right. The middle here is empty, so it does not meet. So let the 32 on the right fill it, and restore it to a complete binary tree. Then this step is to put the final value in the last empty place. This is the corresponding C language code, mainly the lower half. We combine the steps just now. The first is to take out the root node as the minimum value, that is, the value number 1. Next, start the for loop. Here, I is the number of the vacancy, which initially the first one. Then, child is the left child node number of I, which is I multiplied by 2. First, judge whether the right child node is smaller than the left child node. If yes, change child to the number of the right child node, that is add 1. All in all, this is the first step here. Child represents the number of the smaller node. Then, if the value corresponding to child is less than the last value, then it is assigned to the parent node number I, that is upward. Finally, put the final value in the position after all nodes. This is the second step. Okay, that's all for today's video. See you in the next issue.